Okay, in this presentation we are going to look at sampling distributions. So in this example we're looking at the sampling of an exponential random variable, Variates from a exponential distribution. So we have a random variable here, x, and it's distributed as an exponential random variable with rate parameter lambda equals 0.02. So essentially what we're going to be doing is getting some sample means of various sample sizes and compute the various probabilities of it being above a certain sample size and so on. So calculate the following: the probability that x bar, which is the sample mean, is greater than 55 in a group of 100, which is to say a sample of 100 random variates. B, calculate the probability that x bar is less than 53 in a group of 40. The value of x bar such that the probability of x bar being greater than x bar, which is the sample mean and some particular value for the sample mean is what's referenced there, equals 0.1 when n is 65. And the value of n, if the probability of x bar is less than 49, is 0.1. Okay, so it's essentially sampling distribution. So we're going to use the central limit theorem. To solve these problems, we use the properties of the exponential distribution and the central limit theorem. Okay, so x bar, as I said before, is an exponential random variable, lambda equals 0.02. The mean of x, mu, is 1 over lambda, and that is 50. The variance of x, which is sigma squared, is 1 over lambda squared, and that is 2,500. If you recall that that is the mean and the standard deviation of an exponential random variable is the same. Okay, and hence the variance is the square of that. So just a quick recap on the central limit theorem, which is very important in these type of questions. The central limit theorem allows us to approximate the distribution of the sample mean x bar of an exponential random variable regardless of the underlying distribution, the original distribution's shape. Given a sufficiently large sample size, the central limit theorem states that sampling distribution of the sample mean will be approximately normally distributed with mean, mu, and standard deviation, sigma divided by the square root of n, the standard error in other words. Okay, so that's the general approach we're going to take. You probably would be familiar with that already, the central limit theorem and the importance of it, but just to specify it. Okay, so exercise A. Okay, so what we're interested in here is the probability of the sample mean x bar being greater than 55 in a sample of 100, or a group of 100 as it says there. The sample mean x bar for a sample size n can be approximated by a normal distribution due to the central limit theorem, just a statement of what I said previously. X bar is a normally distributed random variable with mean, mu, and variance sigma squared divided by n. Okay. So for n equal to 100, the mean is mu equal 50, and the standard deviation, sigma of x bar, which is the sampling standard deviation, that is sigma divided by the square root of n, which is 50 divided by the square root of 100, which is 50 divided by 10, which is 5. Okay? So we need to find the probability of x bar being greater than 55. So essentially what we're going to do here is use z-scores and the cumulative distribution function of the standard normal distribution. So z equals x bar minus mu divided by sigma of x bar. Okay? And that is 55 minus 50 divided by 5, and that is equal to 1. Okay? So using the standard normal distribution tables, we're interested in the probability of z being greater than 1, z-score, and that is 1 minus phi of 1, where phi is the cumulative distribution function of the standard normal distribution. And that is equal to 1 minus 0.8413, which is equal to 0.1587, which should be a familiar number, really, if you've any practice with the normal distribution. So anyway, the answer is the probability of x bar being greater than 55 is approximately 0.1587, 15.87%. Okay, moving on to the next one now. So the probability of x bar being less than 53, we're going to approach this the same way. Some of the numbers change, but actually it's more or less the same sort of approach. For n equal to 40, mu is still equal to 50. We'll stay 50 the whole way through. The standard deviation will change because are dealing with a new sample size here. So sigma of x bar is sigma divided by square root of n, which is 50, divided by the square root of 40, which is approximately 7.91. So we need to find the probability of x bar being less than 53, and again, we use the z-scores. So z equals x bar minus mu divided by sigma of x bar, which is 53 minus 50 divided by 7.91, and that is approximately 0.38. Okay, so same approach as before. We're going to use the standard normal tables, or the cumulative distribution function, the phi function of the standard normal distribution. Probability of z being less than 0.38 is the phi of 0.38, and that's approximately equal to 0.6480. So the probability of x bar being less than 53 is approximately 0.6480, nearly 65% in other words. Okay, so moving on. You probably notice that these are handy enough, really, if you're familiar with the standard normal distribution and z-scores. So we want to calculate the value of x bar, small x bar, just to specify that it's a specific number that we're looking for, such that the probability of x bar being greater than x bar, and again, x bar, the capital sort of is a name, and small x means a particular number that we're looking for, okay, such that that is equal to 0.1 when n is equal to 65. Okay, so for n equal to 65, mu is always going to be 50, but the standard deviation changes from sample size to sample size. So here, sigma of x bar is sigma divided by the square root of n, and that is 50 divided by the square root of 65, which is approximately 6.20. Okay, so we need to find x bar such that the probability of x bar being greater than x bar is 0.1, small x bar again, just to re-emphasize that. Okay, so if that's the case, what we need is a z-score such that the probability of being in excess of that z-score is 0.1. And if you look up the tables, which hopefully you should be familiar enough with it now, you realize that that z-score is 1.28. So we need a z-score of 1.28. So we're going to use our formula for the z-score to see what value of x bar will give us a z-score of 1.28. So z equals x bar minus mu divided by sigma of x bar. That needs to be equal to 1.28. Working it out, okay, that will give us x bar equals mu plus z times sigma of x bar, which is 50 plus 1.28 times 6.20. And that is 57.94. So the value we're looking for, x bar, is approximately 57.94. Okay, and the last one, something similar again. Okay, the value of n if the probability of x bar being less than 49 is 0.1. So we're going to use a lot of the same approach from the last question. We're just requiring different outputs in this case. Okay, so we need to find n in this case such that the probability of x bar being less than 49 equals 0.1. Okay, so the probability of z being less than z is 0.1. So essentially what we need is a z-score that works out as 1.28, or minus 1.28, I should say. So it's the complement of the z-score we use in exercise C, in other words. Okay. Now, so using the standard normal distribution, z equals 49 minus 50 divided by sigma of x bar. Okay. And that has to equal to minus 1.28. So essentially what we have to do here is solve for sigma of x bar. So minus 1.28 is equal to 49 minus 50 divided by sigma of x bar. So sigma of x bar is 1 over 1.28, which is approximately equal to 0.781. Okay. So since sigma of x bar is 50 divided by the square root of n, essentially what we have here is a value of 0.781. That's our sigma x bar. And that is equal to 50 divided by the square root of n. So what we have to do is solve for n here. So just rearranging that equation, sigma of n is equal to 50 divided by 0.781. 50 divided by 0.781, and that is equal to 64.05. So we have to just square that. So n is approximately the square of 64.05, and that is approximately 4,104.4. So essentially the value is approximately 4,104. You can round it up to 4,105. I don't think that would make much of a difference. It's approximate anyway. So yeah, that's it. We'll leave it there.